Hello everyone. Hello everyone. You are welcome to Warren Science Academy. My name is Michael Warren and I'm the lead tutor at Warren Science Academy, and I'm also your host for this live class. Now in the course of this live class, we are going to have the following topics where we look at the determination of empirical molecular formula, and after which we look at determination of molar and molecular mass. Thirdly, we look at how to balance chemical equation, and lastly we look at the formation of chemical compound. Now it's my hope that at the end of this live class you should be able to do the following on your own comfortably. So we'll begin this lesson by looking at how to determine empirical and molecular formula. So we'll take this off the board and then we'll begin this live class. So when we talk about empirical molecular formula, now what do we mean? Now empirical here just simply means a test, or in essence it means the simplest formula. So now when we talk about empirical formula, what do we mean? Empirical formula is simply, so we'll take definition for empirical formula. So empirical formula is the simplest formula. So there are three key things. It is the simplest formula of any chemical compound, simplest formula of a chemical compound, then secondly, the empirical formula tells us the element present in the compound, element present in the compound, and thirdly, the empirical formula tells us the simplest ratio to which these elements are combined, simplest ratio to which the elements are combined. So now let's break this down. Empirical just simply means a test. It may not be the real thing, but it gives us a clue of what is going on. Do you get now? So when we talk about empirical formula in terms of chemistry, it is the simplest formula of a chemical compound, in the sense that if we have a compound, let's say a compound is C5H10, what is the simplest form? If you remember your primary school, in mathematics, if I have a fraction, let's say 5/10, I can break it down to a very simple form, in the sense that 5 can cancel 5 to give us 1, then 5 can cancel 10 to give us 2. So this is the simplest form of this fraction. So if I have C5H10, I can break down this compound to become C. If I divide both of them by 5, I'm going to end up having CH2. So this simplest form of a chemical compound is what we call empirical formula. Secondly, empirical formula also tells us the elements that are present in the compound. So in this case, I cannot tell that the element present in this compound is carbon and then hydrogen. So this is what an empirical formula also tells us. And lastly, the empirical formula tells us the simplest ratio to which the elements are combined. So in this case, I can see that the ratio of carbon to hydrogen is what? 1:2. So in essence, when we want to define empirical formula, we can therefore define empirical formula as the simplest formula of a chemical compound, which tells us the elements that are present in the compound and the simplest whole number ratio to which those elements are combined. So that is what we mean by an empirical formula. Again, it is the simplest formula. The simplest form to which we can use that formula is what we call the empirical formula. Secondly, the empirical formula tells us the elements that we have in that compound. And lastly, it tells us that simplest ratio to which they are combined. Let's say we have another compound. Let's say we have C3H9. Let's say we have something like this. Now, this could be a molecular formula for something. Now, when we break down this compound to the simplest form, I may end up having CH3. So this simplest form of this compound is what we refer to as the empirical formula. Or let's say we have N2H4. Now, looking at this, 2 can divide both of them. So if 2 divide this, we are going to end up having 1. And if 2 divide 4, we are going to end up having 2. So this compound can be written as NH2 in the simplest form. So this is the empirical formula rather for this compound. Now, there's something you ought to know. Not all formulas have a different molecular or a different empirical formula. For example, we have something as carbon dioxide, and carbon dioxide is CO2. So this is like C1O2, and we cannot break this number, or we cannot simplify it. So in essence, the molecular formula will be CO2. The empirical formula will also be CO2. So there are some compounds that have the same molecular formula as the empirical formula, while some have a different empirical formula from their molecular formula. Now let's come to molecular formula. Now, what is molecular formula? Let's take down that definition. Now, when we talk about molecular is not the true formula. So this is the true formula, and then this is the simplest formula. So we have a true formula and we have the simplest formula. Now I want to talk about molecular formula. So molecular formula is the true formula, or some books might put it as the exact formula of a chemical compound which tells us the actual ratio to which the elements are combined. So for the molecular formula, what makes it different from the empirical formula is that the empirical formula is just the simplest, like the lowest form, while the molecular formula, it is the true formula. So whenever we write out the formula of compound, we are actually talking about their molecular formula and not the empirical formula. So again, for molecular formula, it is the true, or we use another word which is exact, as you see in most textbooks. So it is the true or the exact formula of a chemical compound which tells us the actual. So you see this word keep playing out in definition: true, exact, or actual. But in this case, it tells us the actual ratio to which the elements are combined. So you will now see that the difference between empirical formula and molecular formula is that the empirical formula is the simplest, while the molecular formula is the true formula. So the empirical formula will tell us the simplest ratio, but the molecular formula will tell us the actual ratio to which the elements are combined. So let's say we have a compound. Let's take butane. There's a compound called butane, or a chemical compound called butane. And butane is C4H10. So we have C4H10. This is the true formula for butane, C4H10. So we can rightly call this the molecular formula. But when we break down this ratio, I can see that 2 can divide 4 rather to give us 2. Then 2 can divide 10 to give us 5. So this is the simplest form. It's just like having 4/10. And when I simplify this, I'm going to have 2/5. So this formula is what we can refer to as the empirical formula. So now, what is similar to both the molecular and the empirical formula is that the both of them will tell us the elements that are present. So in the molecular formula, I will see that I have carbon and hydrogen. In the empirical formula, I will also see that I have carbon and hydrogen. But the difference is that one is the simplest, while the other is the true formula of a chemical compound. So whenever you write the formula of a compound, you're actually writing the molecular formula and not the empirical formula. So like I said earlier, some compounds have a different molecular formula from the empirical formula, while some can just be the same. For example, we have what we call carbon 2 oxide. So we have what we call carbon 2 oxide, or the old name is carbon monoxide. Now for both compounds is just the same, just like this what we call the IUPAC name, then this what we call the O name is for the same compound. So this compound is written as CO. So CO simply means that we have one carbon, one hydrogen. So this is already in the simplest form. We cannot break down this, just like having 1/1. We can't simplify this further. So this is the molecular formula. This is also going to be the empirical formula. Or let's say we have a compound which is ammonia. Ammonia is written as NH3. Ammonia is NH3. Now, looking at this compound, we have one nitrogen. Now, take note of something. When you don't have a number, just know that there's an invisible one at that element. So we have one nitrogen, 3 hydrogen. So in this form, we have it as 1:3. And we cannot simplify 1:3 because there's no number that can divide 1 and also divide 3. So that means that it is already in the simplest form. So that means that NH3 is both the molecular formula, let's say MF, and also the empirical formula, let's say EF. So for some compounds, the empirical formula can act as their molecular formula, while for others, they have a different empirical formula from their molecular formula. So now, in your exam, questions are usually asked, or you are being told to calculate either the empirical formula or the molecular formula. So I'm going to give you the entire steps for calculating for either the empirical formula or the molecular formula. So let's go. So there are various steps. So we'll take the steps one after the other. So the first step is that you will divide the percentage of the element. So we are going to divide the percentage, or in most cases the mass, by the what we call the relative atomic mass. Relative atomic mass. And we usually call it ROAM. So in your exam, you could see ROAM. That ROAM there means relative atomic mass. So in our next video, we'll talk about what's called relative atomic mass. So it's just a mass when it is compared to something. So let's just talk about it quickly. So we have what we call relative atomic mass. So in essence, so this is relative, then this is atomic, and then this is mass. So it simply means, taking it from the back, it is the mass of an atom. So mass of an atom, that's why it's called atomic mass. Now whenever you have the word relative anywhere in chemistry and physics, relative means comparing that thing with something else. So the relative atomic mass is just the mass of any element when we compare it with a guy called carbon-12. So carbon-12. So when we look at the mass, let's say we have an atom, let's say hydrogen, and then we have carbon, but it's a form of carbon which is called carbon-12. So when we compare the mass of that atom with an atom of carbon-12, the comparison is what we refer to as the relative atomic mass. So in essence, ROAM is defined as the mass of an atom in comparison or relative to the mass of carbon-12, or when being compared to the mass of carbon-12. So the first thing we do is that we divide the percentage or the mass of the element by the relative atomic mass. Then secondly, we divide by the smallest value. Then thirdly, when we divide by the smallest value, we take the answers as the atoms of the element involved. So we are going to take these 3 steps. Now these 3 steps will help us to calculate for the empirical formula of any compound. So whatever answer you get from step 3 is what we call empirical formula. Then moving on, the empirical formula times n will give us what we call the molecular formula. formula. So we are going to use these steps to answer some chemistry Jamb questions. So I will take the Jamb chemistry past question, and then we'll take some questions and then answer them based on the steps. Now the steps are simple. We are going to divide the percentage or the mass of the element by what we call relative atomic mass. Secondly, we are going to divide by the smallest value, and then whatever answer we get after that division, we form our N, which we call the atoms. And thereafter, if we must calculate molecular formula, we can now move from step 3 to step 4. But at step 3, what you have gotten is your empirical formula. So if the question tells you to calculate the empirical formula, you are simply going to stop at step 3. But if the question asks you to calculate for the molecular formula, you are going to move from step 3 to step 4. So if you are watching this video, I expect you to take note of this, as I'll be taking this off the board so that we can attempt some Jamb chemistry question on this topic. So I have the Jamb Prep 50 here with me, as I'll be taking some Jamb chemistry questions so that we can understand this concept properly. So we'll be taking some questions, and I will highlight the years so that you can always go back and make reference to those questions. So we'll be taking our first question from Jamb 1985 question 13, and I will put the question on the board. So the first question we have from this topic says that an organic compound, so we have our first question, question 1, which says an organic compound. An organic compound contains 72% carbon, and thereafter we have 12% hydrogen and we have 16% oxygen by mass. Now the question tells us to calculate the empirical formula, and in your exam they'll most likely give you the relative atomic mass for the element. So here carbon is 12, hydrogen is 1, and then oxygen is 16. Now the question tells us to calculate the empirical formula of this compound. Now this is a Jamb question 1985, so this is UTME 1985 question 13. So we are going to attempt this question right now. Now how do we attempt this question? Again, remember your steps. I gave you 4 steps, but the first 3 will help us to calculate the empirical formula, then the last will help us to calculate the molecular formula. Now when we look at this question, we are being told that this compound contains 72% carbon, then we have 12% hydrogen, and last we have 16% oxygen. So what are we going to do? Now we already know the element present, and the element present here are carbon, hydrogen, and oxygen. So we have carbon, we have hydrogen, and then we have oxygen. Now the percentage of carbon in this compound is 72%, and then that for hydrogen is 12%, and for oxygen is 16% rather. So this is 16%. Now how do we calculate empirical formula, which this question tells us to do? Now the first step, if you go back to the rules I gave to you, is that you are going to divide the percentage, or it could be the mass sometimes, by what we call the relative atomic mass. And the relative atomic mass is what I've been giving to us in this bracket. Now, so we are going to divide carbon by 12, and then we are going to divide hydrogen by 1, and then we'll divide oxygen by 16. So this is the first step. So again, the first step is divide by the relative atomic mass. That's the first step. So we are going to divide each of these. So we have 72 divided by 12, and that will give us 6. So this is 6. Now 12 divided by 1 will give us 12, and 16 divided by 16 will give us 1. Then what do? We are going to divide all through by the smallest. So I'm going to divide this by the smallest between 6, 12, and 1 is 1. So divide by 1, divide by 1, and divide by 1. So here it's going to be divide by the smallest value. Smallest value. Now 6 divided by 1 is 6. 12 divided by 1 is 12. And then 1 divided by 1 is 1. So when we get this is going to be our ratio. And as you can see, this is the simplest ratio because there is no other number that can divide 6, 12, and 1 at the same time. So since we have gotten this answer, we are now going to pair them to the atoms that, or the elements rather, that they follow. So this is going to be 6 atoms of carbon. So our final answer will become C6. Now for hydrogen, we have 12. So this is going to be H12. And for oxygen, we have 1. So it's going to be O. So in this case, this is the empirical formula for this compound. So I hope you found this easy. So please, if you have any question, any comment or suggestion, do it to leave them in the comment section as I'm checking that as soon as possible. I'll check that as soon as possible. So we'll take a second question and then we'll move on to the second aspect of this class. So in our second question, we are going to take a question that has to do with the molecular formula. Again, I gave you 4 steps, but the first 3 will help us to calculate the empirical formula, just like we did. And then the last one will help us to deduce the molecular formula. So we are going to take the last question on this particular subtopic. And I hope in subsequent videos, we also look at more examples on empirical formula and also on molecular formula. So our second question is from the Jamb past question 1984 question 28. So question 2. The question 2 which says that an organic compound with a vapor density the vapor density 56.5 has the following percentage composition. Has the following percentage composition, and the percentage composition we have says that C is 53.1%. And then we have N, which is nitrogen, to be 12.4%. And then we have oxygen to be 23.8%. And then we have hydrogen to be 6.2%. Again, the question is clear. It says calculate the molecular formula. And in brackets, we are given the relative atomic mass of the various compounds. We are given the RAM of nitrogen to be 14. So nitrogen is 14. Then we have carbon is 12. Then we have oxygen, which is 16. And then we have hydrogen, which is 1. So this is a Jamb question. So this is from the Jamb past question 1984. And this is question 28. So you can always do it to reference the question as you will need them. So we are going to attempt this question, and we have this entire question, which is a question on molecular formula. So again, when given, the first thing you ought to do is to identify the element involved. Now when you read through the question, we'll find out that the elements involved are carbon, nitrogen, oxygen, and then hydrogen. Now, this question is a beautiful question, especially when you have a good knowledge of organic chemistry. Now, in organic chemistry, we have 2 major elements, which is carbon and hydrogen. Next, the next major important element you find out is oxygen, and most times or sometimes you find nitrogen. So I like saying chon, C-H-O-N. So it gives me a proper arrangement of how elements are arranged in organic compound. So the two most important elements are carbon and hydrogen. Then sometimes you find oxygen and rarely nitrogen. So I will arrange this element in that format. So we have carbon, we have hydrogen, we have oxygen, and then we have nitrogen. Now the percentage for carbon is 53.1%, and then for hydrogen it is 6.2%, for oxygen it is 28.3%, and then for nitrogen it is 12.4%. And you know the drill. The first step is that you are going to divide this percentage composition by their relative atomic mass. So I'm going to divide this by the relative atomic mass for carbon, which is 12. Now for hydrogen is 1, for oxygen is 16, and then for nitrogen it is 14. Now for those persons that are writing certain exams like Jamb and then some advanced exam, I will urge you that you take note of the various relative atomic mass, because in some exams you might not be given. So it's very good you know the relative atomic mass for some common elements like carbon, hydrogen, oxygen, chlorine, and the likes. So now the first step in solving this question is to divide by the relative atomic mass, which we have done here. So I will divide and then impute the values. So we have 3.1 divided by 12, which is about 4.425. So this is 4.425. So this is a point. Then this will give us 6.2. Then we have 28.3 divided by 16, which is 1.77. And then we have 12.4 divided by 14, and that will give us 0.89. Now when you have done this, the next thing you ought to do ideally is to divide by the smallest. Now we can easily know which is the smallest by looking at their whole number. This is 4, this is 6, this is 1, and this is 0. So ideally I'm going to divide with this one, which is the smallest. So I divide all through by the smallest, which is 0.89, 0.89, and then 0.89. So ideally this will give us 1 ratio. So this will be 1.77 divided by 0.89, and this will give us approximately 2. And then for this we have 6.2 divided by 0.89, and this will give us approximately 7. And then when we divide for 4.425 divided by 0.89, this will give us approximately 5. So now we have this as the simplest whole number ratio: 5:7:2:1. So now I can now impute this. So now I have C5H7O2 then N. But this is our empirical formula. This is not the molecular formula. So this is the empirical formula. Now the question did not tell us to calculate for the empirical formula. The question says calculate the molecular formula. So we cannot stop there. And now there's a formula for calculating molecular formula for empirical formula. And like I said in the previous step, we said empirical formula. I'll just write the formula again. Empirical formula times N is equal to what we call the molecular mass. Molecular mass. Now, but if you look at this question, they didn't give us molecular mass. Rather, they gave us something very unique. And that unique thing is what? Vapor density. So how do we then calculate molecular mass? That leaves us with the question, but it is very easy. Now, there's a formula for it. The formula says that molecular mass is equal to 2 times what we call vapor density. So a way to calculate for the molecular mass, which we are not given in this question, is to multiply this vapor density times 2. So and how do we do that? Let's go. So the molecular mass will be 2 times our vapor density in this case is 56.5. So I'll give us 56.5 56.5. So now we are going to multiply, so we cannot tell what the molecular mass will be. So 56.5 times 2 will give us 113. So the molecular mass, without wasting time, is 113, and it has a unit which we call gram per mole. So this is the unit for the molecular mass. But we are not looking for molecular mass, rather we are looking for molecular formula. So now let's calculate that molecular formula. So I have to take this off so that we can therefore get our answer. Now, we have this formula which we are going to use. So again, the formula is empirical formula times N is equal to molecular mass. Now the empirical formula from our calculation is C5H7O2N. Close your bracket. There's an N outside, is equal to molecular mass, which we calculated first, 113 gram per mole. Now what do we do? Because we are talking about mass, we are going to be calculating the mass of everything here. Now carbon, if you remember, is the relative atomic mass is 12. So this is going to be for carbon 12 times 5 plus for hydrogen, if you remember, it is 1. So that's 1 times 7. So if you remember, I wrote some things in the bracket. So what I wrote in bracket is what we call the relative atomic mass. Then for oxygen it is 16. That is 16 times 2. Then for nitrogen it is 14. That's 14N. Let's close the bracket. It's equal to 113. So we are going to calculate. So I'm just going to calculate everything straight. So 12 times 5 is 60. So I'm going to enter 60. Then 1 times 7 is 7. Then 16 times 2 is 32. Then plus whatever answer we get, we are going to add it to 14. So let's just say plus 14. And that will give us 113. So when we solve for everything in the bracket, we are going to have 113. Now there's an N outside, it's equal to 113. So when you divide by 113, divide both sides, just as you do in mathematics. Therefore, N will be equals to 1. So what does that mean? I'm going to replace this N with 1. So we now have this as C5H7O2N. Close that bracket. Instead of writing N, I'm going to replace it with 1. Now from here we have 5 times 1 will give us 5. 7 times 1 will give us 7. 2 times 1 will give us 2. And then 1 times 1 will give us 1. So this is going to be the final answer. So in this compound, the empirical formula is the same as the molecular formula. So this is the molecular formula. So basically, like I said earlier, some compounds have their empirical formula to be their molecular formula. So this is how we calculate empirical formula from, or this is how we calculate molecular formula from the empirical formula. Now let me just give you an hint. Probably you solve, and let's say we are having C2H3, and when you calculated, N was 2. So let's say N is 2. So in this case, I'm going to say 2 times 2, which will give us 4. Then 3 times 2 should give us 6. So if you have any number greater than 1, it's just a simple mathematics. Multiply the number outside with the number inside, that is the atom, and then you get your molecular formula from the empirical formula. Again, if you have any question or comment or suggestion, do it to leave them in the comment section just beneath the live video, as I will attend to all questions shortly. So we'll move to the next aspect of this class, but before then, let me check the comment section if there are any questions. Okay, in the absence of any question, we'll move to the second aspect of this class, which is the calculation of molar or molecular mass, and it's a basic, important, and simple aspect of chemistry. So the second part of this lecture, of this lesson, we focus on the calculation of molar, or we can term it the molecular mass. We are going to look at how we calculate the molar or the molecular mass of compound, and it's just a very easy concept. So I will explain it in a very easy way so that we can know what it entails. Now just imagine you went to the market and you bought eggs. Let's say you bought 3 eggs. 3 eggs. And then one egg, for example, one egg is sold at, let's say, 15 naira. And then you bought, let's say you bought 2 drinks, for example, alongside, and then one bottle of that drink is sold at, let's say, 100 naira. So this is everything you bought. So this is everything as a whole. So when you are going on, you are taking everything alongside. So we can tag this as 1 mole, or we can tag this as 1 molecule. So what is the cost of everything? So if this happens in chemistry, we'll call this the molecular cost. But since we are talking about mass in chemistry, we'll call it the molecular mass. So for example, I can say, okay, since 1 egg worth 15 naira, that means the 3 egg will cost 115 naira. 150 naira. Then if 1 bottle of a drink costs 100 naira, that means these 2 bottles will cost 200 naira. So at the end of the day, this will give us 350 naira. So this is the cost of this entire composition. So that entire composition is what we call a molecule or a mole. Now, so if it happens in chemistry, the mass of that entire guy is now what we refer to as the molar mass or the molecular mass. So if I have just H alone, this is just an atom of hydrogen. But if I have an H and that H together, this is no longer an atom because I've now added some things together. So we write this guy as H, but this I've written as H2. So this is what we call 1 mole of hydrogen. This is now what we call 1 mole of hydrogen. So the mass of a mole is what we call the molar mass. Or if we have molecule, we now call that the molecular mass. Molecule is just when you now have different elements. For example, I have H2O. This is a combination of hydrogen, 2 atoms of hydrogen, and then 1 atom of oxygen. So we call this 1 molecule of H2O is water. So this is 1 molecule of water. So in essence, molar and molecular mass is just a mass of the various atoms, the total mass of the various atoms or elements that make up that particular compound. So we are going to move on to look at how to calculate simple molar and molecular mass. So we are going to take this particular question so that we can understand this concept. So we'll take just 2 questions and then we'll move to the next aspect of this class. So the next thing we are going to look at is we'll take a question which I'll modify so that we can understand this concept. So I'm going to modify the Jamb 2015 question for us to understand this particular topic. So question 3 in this class becomes calculate the molecular mass of glucose. And glucose is C6H12O6. So in brackets, the mass of carbon is 12, hydrogen is 1, and then oxygen is 16. So we are going to look at how to calculate the molecular mass of this compound, which is glucose. Now, glucose is C6H12O6. Now, for you to be able to calculate the molecular mass, you must know your molecular formula. So it is the mass of that formula that we call the molecular mass. Now let's go ahead to calculate this. So the molecular formula is what? C6H12O6. So what do we do? Now this tells us that one atom of carbon is 12, but mind you, we have 6 atoms. So the mass of these 6 atoms will be 12 times this 6. So if one is 6, if one atom of carbon is 12, the 6 will be 12 times that 6. Now hydrogen, one atom is 1, but we have 12 atoms of it. So this is going to be 1 times 12. Then for oxygen is 6 atoms here, but 1 is 16. So this is going to be 16 times 6. I hope that's clear. So now 12 times 6 will give us 72. Now 1 times 12 will give us 12. And then 16 times 6 will give us 96. So then we are going to add up everything together. So this 4 plus this, that's 10. Then we have 8 plus that 1, that's 9 plus this, that's 18. So our final answer becomes 180 grams per mole. So this is how we calculate molecular mass from the molecular formula. So we'll take another question so that we can understand this concept as a whole. So we'll move on by taking as fourth question. So we'll take the fourth question in this case. So we are going to take a question which is basically easy. So the fourth part of this, the fourth question, so let's see that as question 4. So the question says calculate the molecular mass of tetraoxosulfate 6 acid of tetraoxosulfate 6 acid. So this is H2SO4. And there's one important thing you ought to know. Most times in your exam, you could be given a question like this without the molecular formula. So it is your duty to know the molecular formula, or if you can't do that, you ought to derive the molecular formula when you are giving the name of that compound. So the third part or the fourth part of this class will focus on that aspect, how you can know the molecular formula when you are giving the names. So now let's take down. So hydrogen is 1, sulfur is 32, and then oxygen is 16. So again, first thing is that you must know your molecular formula, which we have there as H2SO4. So the molecular formula is H2SO4. So this is the molecular formula. So now again, we have 2 atoms of hydrogen, 1 atom of sulfur, and then 4 atoms of oxygen. But mind you, just 1 atom of hydrogen is 1, but we have 2 atoms of it, so that's going to be 1 times 2. Then for sulfur, we have just 1 atom of it, so let's say plus 32, since we are not multiplying by any number that is more than 1. Then for oxygen, we have 4 atoms, but 1 atom is 16, so I'm going to say 16 times 4. So this is going to be 2, this is going to be 32, then this is going to be 64, and then we'll just simply add up. Then this will be 34 plus 4, and then this will give us 98. That's going to give us 98 gram per mole. Or some person might write it as 98. In indices, we write as mol raised to the power of -1. So any of them is correct. So basically, calculating molecular mass from their molecular formula is just simply multiplying the number of atoms you have times the relative atomic mass. So the number of atoms times the relative atomic mass, and then we are just simply going to add them together, because it is the total mass of the various elements or atoms you have in that particular compound. So this is how we calculate molar or molecular mass. Now, for a good case of molar mass, you could be given chlorine. So let us take a fifth question. So I'll take it here. So we told to calculate the molar mass of chlorine gas. Molar mass of chlorine gas. Chlorine gas. And then bracket, we told that Cl is equal to 35.5, for example. Now, chlorine gas is not Cl, because Cl is an atom of chlorine, but Cl2 is chlorine gas. Now, there's one important rule I'll leave you with, which is very, very basic. Every gases, or let's leave it at this point, most gases are diatomic. Very important point. So most gases, so let me write here, most gases are diatomic. Most gases are diatomic. Now, what do we mean by diatomic? Di means two. So most gases exist in a paired atom. They usually exist as two guys together, two atoms, diatomic, two atoms together. So chlorine will not be Cl, but rather it will be Cl2. So that means two chlorine atoms have been bonded together. Now, so for Cl2, the mass will be, one atom of chlorine is 35.5. So it's going to be 35.5 times the number of atoms which we have here as 2. And when we add up this is going to give us 71 gram per mole. So this is the molar mass of chlorine gas. So in essence, it's just simply multiplying the number of atoms you have times their relative atomic mass. So if you have any question, comment or suggestion, do it to leave them in the comment section beneath this video lesson. And also, if you are new to this channel and you haven't subscribed to this channel, do it to click on the subscription button somewhere around this video, and I want to see you in my subsequent videos. So let's move on. So we'll move to the third part of this video lesson. So in the first part of this video lesson, we have been able to establish the difference between empirical formula and molecular formula. And then in this section, we have been able to establish how we can determine the molar mass or the molecular mass. And the third part of this video, which we are going to use to conclude this video lesson, is looking at how to balance chemical equation. And this is one very important aspect most students find difficult. And because of this video lesson, we are going to look at a very simplified way we can balance chemical equation. So we move on to look at that aspect. So we are going to look at that aspect, which is balancing of chemical equation. So the third portion of this lesson is balancing chemical equation. So this is the third part of this lesson. Now, what are chemical equations? Let's start with that part. Now, what about a chemical equation? First of all, there is the part equation. Equation just simply means equal. It means what I have here should be what I have here. So it's just like we have a scale, and the scale is like this. It means it's not equal, or like this means not equal. But when it's like this, we can now say that, okay, what I have here is the same thing as what I have here. So that now makes that stuff equal. Now, but in chemistry, what about the chemical equation? It is simply a representation of a chemical reaction. That's the base definition. So a chemical equations are written representation of a chemical reaction. Now, when we take chemical substance in the lab, we take substance A and substance B, and then we mix them together, we bring them together. So many things will happen. Now, we might not be able to see what has happened, but now we can write what is going on. We can tell that, oh, probably if I take hydrogen gas and then oxygen gas, and we end up having water. So now this reaction is being represented in this written format. So a written representation of a chemical reaction is what we call a chemical equation. So the equation tells us so many things which we are going to look at in the course of this live video. So first of all, this is a chemical equation. So it is a written expression of a chemical reaction which we have seen here. This reaction now tells us that when hydrogen reacts with oxygen, I'm going to get water. Perfect. Now, in every chemical equation, we have something on the left-hand side. So we call this LHS, which is left-hand side. Then there are some things on the right-hand side, RHS. Now, what is their name? The one on the left-hand side is what we call reactant. And on the right-hand side, we have what we call product. So we have reactant on the left-hand side and then products on the right-hand side. A good example is just when you make tea. I take milk, and I take chocolate, and then I mix them together and I end up having tea. So this is what we mean by a chemical reaction. In the written form, it becomes a chemical equation. So on the left-hand side, we have what we call reactant, what is reacting together, what is missing. Now, what they produce at the end of the day is what we call product. So in simple terms, a chemical equation consists of a reactant on the left-hand side and then product on the right-hand side, or better still again, reactant on the left-hand side and product on the right-hand side. So that's just what we mean by chemical equation. Now, but moving on, why are we looking at balancing of chemical equation? If I take, let's say, I have a basket, and this basket, there are 2 oranges, for example, or let's say 3, and I have another basket, and in this basket, there are 4 oranges, for example, 4, and I put these baskets together, I bring them together, I react them together, or I mix them together. At the end of the day, I should have a basket that should contain these 3 and this 4, so I should end up having something that has 4 oranges. So what does that mean? I have 7 oranges on this side, 7, and then I have 7. I can therefore see that it's equal. Nothing should be missing, nothing should be lost. Or let me give you another example. I have 1 liter of milk, for example, 1 liter of milk, and I have another liter of milk, 1 liter of milk, for example, 1. So 1 liter, and I mix them, or rather, or let's say chocolate, for example. So let's make it realistic. So, and I mix them together. And then I should end up having 2 liters of tea. So why are we looking at balancing? Because I have 2 before and then I have 2 after. So in essence, in balancing of chemical equation, it means that whatever we have on the left-hand side, the total mass, the total volume of what we have on the left-hand side should also be equal to the total mass we have on the right-hand side. And now this is very important for one reason. And what's that reason? It's very important because in chemistry, there's a law that is called the law of conservation of mass. And I'll write that on the board. So we have this, which is called the law of conservation of mass. Now, this is basically, so we have a law which is called the law of conservation of mass. we have that called the law of conservation of mass. Now, what does this law state? The law states that mass can neither be created, mass can neither be created nor destroyed. So it's a very simple law. It's a very simple law which is relevant in chemistry. It's basic. The law says that mass can neither be created nor destroyed. It means we cannot create mass and then we cannot destroy mass. So if I have 1 gram of a substance plus 1 gram of another substance, I expect that at the end of the day I should have 2 grams. Nothing should be added, that means we cannot create, and nothing should be lost, that means mass should not be destroyed. So you have 1 here, 1 gram, and I have another 1 gram. At the end of the day, I should have 2 grams. Now, in your exam, you could be asked this question: balancing of a chemical equation obeys which law? The law it obeys is what we call the law of conservation of mass, because every balanced equation, as far as that equation is balanced, it is obeying the law of conservation of mass. So when asked that question, your simplest answer to that question is the law of conservation of mass. So let me give you a good instance of what we are trying to talk about. I have the reaction for water, which is H2 plus, let's say, O2. Now this will give us H2O. So that's for water. Now if we look at this, we have 2 atoms of hydrogen, that is 2H. 2 atoms of what? Hydrogen. Now, but on the right hand side, because remember, for an equation to be balanced, what we have on the left should be equal to what we have on the right. I have 2 here, and then I also have 2 here. So for hydrogen, it is equal. 2 on this side, 2 on the other side. So that's perfect, balanced. But for oxygen, I have 2 atoms here, and I have 1 here. So this becomes a problem, and now we are worried it's not balanced. So the equation is what? Tilting towards one side. So we have to ensure that it is stable. So that's why we are looking at the balancing of chemical equation. But let me shock you. If I had 2 here, and then I had 2 to this side. Now let's see, something has changed, but let's see if it makes the equation balanced. Now for hydrogen, I have 2 atoms, and I have 2 moles of this entire guy. So this is going to be 2 times 2, and that's 4. So I have what we call 4 atoms. So what this means, this is H2. H2, this is what H2 means. But now I have 2 of it, that's HH again. So this is H2. So in essence, I have 1, 2, 3, 4. So I have 4 atoms of hydrogen. Remember, I told you that most gases are diatomic, so that's why it's H2. But I have 2 of it, that's this and another one, 1, 2. Now for oxygen, it's just something like this: 2 atoms of oxygen. 2 atoms of oxygen. Now for this side, again, this is 2 times 2, that's 4 atoms of hydrogen. Now for these two affect both the hydrogen and also the oxygen. Now 2 times, there's a 1 here. 2 times 1 is 2, so I have 2 atoms of oxygen. So again, I have 4 atoms of hydrogen here and 4 atoms on the right. So 4 on the left and 4 on the right. Then for the oxygen, I have 2 on the left and then 2 on the right. So whenever we have this, we can now say that this equation is balanced. And since this equation is balanced, it obeys the law of conservation of mass. Again, every balanced chemical equation obeys your law of conservation of mass. So let's look at how we can balance far more complex equation than what we have on the board. So we look at a method or an approach which we call the algebraic method. So let's go. So the method we are going to look at is what we call the algebraic method. So we are going to balance some few equations, and that will bring this live video to a close. Now, what's the algebraic method? In mathematics, algebra just simply means using letters A, B, C, D down to Z as the case may imply. So we are going to take our first question. So question 5 or 6 rather becomes balance the equation. We are going to take a very simple equation, balance the chemical equation. And our equation is what? H2 plus O2 will give us H2O. So I'm going to balance that equation again so that we can understand what this method entails. So we'll talk about the balancing of chemical equation, why it is important. It's important so that we obey one of the laws we have in chemistry, which is the law of conservation of mass. Secondly, it's also important so that whatever we have on the left hand side should be equal to whatever we have on the right hand side. Again, whatever you have on the left hand side is what we call reactant, and then what you have on the right hand side is what we call product. Now, this is an equation, and how do we balance it? Using one of the simplest method of balancing chemical equation, which we call algebraic method. It's a very simple approach. Now, the first thing, which is step number 1, you will identify the element present. Now, what are the elements present? We have hydrogen and then oxygen. So you write them out, hydrogen and then oxygen. So this is what we have in this case. So when we have done that, we are going to ask ourselves, what are the various gases? We have hydrogen here, oxygen, and then water. And you are going to give them alphabet. That is why it is called the algebraic method. So this is going to be A, this is going to be B, and the last one is going to be C. So again, I'll go through the step. Step number 1, identify the elements you have and write them out. So we have hydrogen, and then we have oxygen. Identify them and write them out. Second thing, give them alphabet. That's why we call it the algebraic method. So the next thing I'm going to do is we are going to multiply. Now, you are going to start with the first element or compound, as the case may be. So we have 2 times A, and that gives us 2A. So this is where we have hydrogen here, we don't have here. Then this sign means an equal to, so I'm going to write equal to here. Then on the right hand side, we have 2 times C, that gives us 2C. I hope that's fine. Then for oxygen, we have 2 times B, and that gives us 2B. There's no oxygen here. They will come here, which is equal to, and then move to what we have after the equal to. For the equal to, we have 1 here. If you don't have any number, just know you have a 1 here. Then 1 times C will give us C. So that's what you do. Again, the steps we have taken so far. The first is to identify the element and write them out. Secondly, give them alphabets. A, B, C, D. You can even go down to E, F, G, H, depending on how long the equation is. Thirdly, you are going to multiply the numbers by the alphabet. For hydrogen, it is 2 times A. There's no hydrogen here. They move here. But remember, this sign is an equal to. For this is 2 times C, that's 2C. For oxygen, it is 2 times B, 2B, then 1 times C, which is C. So that's what we do for this chemical equation. So the next thing you're going to do is very simple. You can pick any alphabet, that's step 4. Pick any of the alphabet and equate it to be any number. But it's very good if you use the smallest number, which is smallest positive number, which is 1. So pick any alphabet. You can pick A, you can pick B, or you can pick C. But for me, let's pick A. So let's go. So let A be equals to 1. So we have accepted that this is 1. So what we have here is 2A is equal to 2C. And we accepted A to be 1. Sorry, not the entire 2A. We have accepted A to be 1. So in place of A, I'm going to write it as 1 equal to 2C. Now 2 times 1 is 2 equal to 2C. Then we divide both sides by 2. This will cancel this. When you cancel that, C is equal to 1 because 2 divided by 2 will give us 1. So that's what we do for that entire expression. So again, the basic thing is that you pick any alphabet, either A, B, or C. Some players can choose to start with A, some can choose to start with B, some can choose to start with C. Make it to be equal to any positive number, either 1, 2, 3, 4. You can even make it to be 10. But it's good if you work with the smallest number so you don't start having large values. So for me, I like starting with 1. So I choose A to be 1. So 2 times A, which is 1, for me is equal to 2C. Then when you multiply and divide, you end up getting C as 2. Then there's one thing we don't have, which is B, because we have A, we have C, and then one more thing is left, which is B. So now to get B, let's pick this equation, because this is where B is. So 2B is equal to C. And from our previous calculation, C is 1, so 2B is equal to 1. Then we'll divide both sides by 2, 2. This will cancel this. Then B is equal to 1 over 2. So at the end of this calculation, we now have the values for A, B, and C. But there's one issue we have. We have B as a fraction, and it's not ideal to put a fraction in a balanced equation. So what are we going to do? Let's go. So we have A to be 1, we have B to be 1 over 2, and then we have C to be 1. Now, what are we going to do? To remove this fraction, because we don't like the fraction, we are going to look at the fraction and look at for the denominator. So what is our denominator? Remember, our denominator is the number you have below. The one you have above is numerator. The one you have below is denominator. So you are going to use that denominator to multiply everything. So I'm going to say this is times 2, which will give us 2. I'm going to say this is times 2. 2 cancel 2 is 1, so this is 1. I'm going to say times 2, which will give us 2. So that now brings A to be 1, A to be 2, B to be 1, and then C to be 2. So from there, we can now come and replace this alphabet. Now A is 2, so it's going to be 2H2 plus B is 1, so you will know it to write the 1. So let's write as O2. And then C is 2, so it's going to be 2H2O. So this is how we can balance a chemical equation. So it's basic. We can now check if it's balanced. 2 times 2 is 4. So we have 4 atoms of hydrogen. So 4 atoms. For this, 2 times 2 is also 4. Then for this is just 2. 2 times 1, which is 2. Then for this, 2, there's a 1 here. Times 2, which is also 2. So you can see 4 hydrogen here, 4 hydrogen here, 2 oxygen here, 2 atoms rather, 2 atoms on the right hand side. So we'll take one more question, and then that brings us to the end of this lesson, as we'll take the last topic, which is balancing of chemical equation in our next class. So we take our last question from the Jamb past question, from Jamb 2007 question 2. So let's take that. So the last question in this lesson, which is question 7, is going to be, we have a question which is MnO2 plus, we have X, we don't know what X is, XaCl to give us MnCl2, then we have YH2O, this water, this is Y, so let's put it in a better form, YH2O, and then lastly we have ZCl2. Now the question says from this equation, what are the values of X, Y, and then Z? So I think that's all, respectively. So the question says, what are the values of X, Y, and Z? So we'll look at this question using a method which we call the algebraic method. Now let's go. So we have MnO2. Again, what is the step? The first thing is that you are going to identify the elements present in this equation. So first of all, we have Mn, which is manganese, Mn. And then we have oxygen, which is O. We have hydrogen, which is H. And lastly, we have chlorine, which is Cl. Now, in this case, there are some things that are missing. They only give us alphabet for this. So they give us alphabet for this, and alphabet for this. but we are going to complete it. So I'm going to add A to this, which might not need, and then I'm going to add B to this. But mind you, the question told us to look for X, Y, and Z. But we just need to complete it so that we can find the values of the other ones. So again, the second thing we are going to do after writing them out is to multiply them with the alphabet. So for manganese, we have 1 here. 1 times A is A. There's no manganese here, so we move to this, which is equal to. Then for this, we have 1 times B, which is B. That's for manganese. So we have settled this and we have settled this. Next, for oxygen, 2 times the alphabet before is 2A. There's no oxygen here. Then we'll move to here because there's no oxygen here. Then we'll come here. For here, we have 1 times Y, which is Y. Then we have settled that for oxygen. Then for hydrogen, we have 1 atom of hydrogen times X, which is X. Then there's no hydrogen here, there's none here, but there's hydrogen here. Then 2 times Y will give us 2Y. Then the last element is chlorine. For chlorine, 1 times X will give us X. And then we have chlorine here, and then we have chlorine here. For chlorine here, this is going to be 2 times B. That will give us 2B. Then we are going to say plus, because there's no equal to now. We have written this equal to here. After the chlorine here, 2 times B, there's another chlorine here, 2 times Z, that's 2Z. So this is going to give us 2Z. So this is a different case from the previous question we looked at. So again, the rules still stand. After our second part, the third thing is to pick any of the alphabet, any of them, and make it to be equal to 1. So for me, I like picking A, and I like making it to be equal to 1. Somebody can make it to be equal to 2, 3, 4. But remember, stick with the positive number, and always try to use the smallest positive whole number. So let's start with A. So let A be equals to 1. So from our first equation, A is equal to B. And already we have defined A as 1. So 1 is equal to B. That means that B is equal to 1. So this is the first. So A is equal to 1. B is equal to 1. Then we'll move to the next one, the next equation. This one equation which we have solved out, which we have sorted out. Then we have this, which is 2A is equal to Y. Now A, from our first definition, we say let A be equals to 1. So this is 2 times 1 is equal to Y. Therefore, Y will be what? 2 times 1, which is 2. So this is Y. So we've sorted that out. Then this is the next part. The next part says X is equal to 2Y. So X is equal to 2Y. Now, we don't know X, but we know Y. So this is going to be X is equal to 2 times 2. And 2 times 2 is what? 4. So therefore, X is equal to 4. So we have A, B, Y, and X. Then there's one thing left, which is Z. So let's take this equation. So that equation we have now is X is equal to 2B plus 2Z. So we have X is equal to 2B plus 2Z. So this is the equation we have in this case. So now what are we going to do? So we are just going to play with it as normal mathematics. We know what X is, which is 4. So this is 4 is equal to 2. We know B here to be 1. So that's 2 times 1 plus 2Z, which we don't know. Now this is 4. 2 times 1 is 2 plus 2Z. Now we are going to collect like terms, just as we do in math. So I'm going to take this 2 here. It's going to be 4 minus 2 is equal to 2Z. And 4 minus 2 is 2. 2Z. Then we divide both sides by 2. 2 will cancel 2. Then Z is equal to what? 1. So this is our final answer. So if you look at all the answers we have A to be 1, B to be 1, Y to be 2, X to be 4, Z to be 1. So if you look at, they are all whole numbers. So there will be no need to multiply anything by any number. So the last thing we are going to do is to replace each of them. So A is 1. So this is 1. X from our calculation is 4. Then B from our calculation is 1. Then Y from our calculation is 2. Then Z from our calculation is 1. So in this question says find X, Y, and Z x is 4, y is 2, and then z is 1. So in your exam, your answer should be 4, 2, 1. Because of this word is here, which is respectively. So respectively means arrange them in the right order. X is 4, y is 2, then z is 1. So in exam, more especially the UTME, you will see questions like A, let's say A, 4, 1, 2, B, 2, 1, 4, for example, C, 4, or let's say 2, 4, 1, and then you can see D as 4, 2, 1. Don't think that they are all the same. Don't say, oh, probably just a mistake, and then you end up picking A. The word respectively means in the right order. So the right order should be 4, 2, 1, and not 4, 1, 2. So viewers, I hope you enjoyed this particular video lesson and you learned a lot, all the way from the determination of empirical molecular formula. Here we say the empirical formula is the simplest formula and molecular formula is the true formula. And then we looked at some certain steps for calculating empirical molecular formula. And then we move on to look at how to calculate molar mass and molecular mass. And then lastly, we look at some series of steps for calculating or for balancing chemical equation. And we said a balanced chemical equation obeys the law of conservation of mass. And this is very, very important because whatever we have on the left hand side should be equal to what we have on the right hand side of a chemical equation. So till you get to join the next live class or you get to see my next video, do have a wonderful time.